Hello friends, welcome to today's tutorial. Today we shall be dealing with influence line for continuous beam, and we shall be treating three span beams. Now we are going to do the influence line diagram for moment at point K. Now when you look at the board, we have a continuous three span beam, 10 meters, 20 and 10 meters respectively. Now we are going to draw the influence line diagram for moment at point K. Now in doing this, the first thing we are going to do, we are going to introduce a hinge at point K. And point K is 4.493 meters away from point A. 4.493 meters away from point A. Now the first we are going to do, we are going to determine the maximum moment at point K. Now, obtaining the maximum moment at point K due to series of moving loads, we are going to apply a hinge at K. So when we apply a hinge at K, and we are going to equally apply a couple moment at point K. So applying a hinge at point K and a couple moment at point K, we are going to have it as this. We have a couple moment. Is the couple moment. Of course, when we have an hinge at that point K, we're going to see the reactions at point K in opposite directions. We have this one coming this way. Well, let's call it, we can call it arrow K, whichever, whatever you want to call it. Here remains point arrow A. Let's call that point reaction arrow A. So we have arrow K. Let's call it arrow K prime. Okay. At this point, we have, let's call it arrow K prime prime. Arrow K, call it arrow K prime prime. Now the next point we have arrow B, reaction at B. We have reaction at C. Then the last we have reaction at point D. So this is a free body diagram. Of course, the couple moment is a unit couple moment, so 1 kilonewton meters in both directions, both clockwise and anti-clockwise direction. So having drawn this free body diagram, remember we are going to have what is left over here to be 5.057 meters if the entire span is 10 meters. Okay. So having done this, let's bring out the figures. Yeah, remember it's 20 meters. Yeah, 10 meters. Okay. So the next thing we're going to do is to obtain the reactions of the beam. Now the beam has been divided into two parts, as you can see. So we're going to obtain the deflected shape. Remember, the deflected shape of the continuous beam due to the application of a couple moment at that point K will give us the influence line diagram for this beam at point K. So We have it as this. So let's draw it. We'll call here support. Put the supports. We have the last with support D. So let's label it. We have support B, C, and D. Okay. So this is what we have as the deflect. This is what we have as the beam. So next thing we are going to do, let's bring point K. We want to draw the deflected shape. So this is how it goes. You see, deflects this way. It's deflecting in the anti-clockwise direction. So let's trace it down to K. We have it as this. Okay, turning over in the anti-clockwise direction. Now let's get the other side of the beam. So let me pick it from, you can see the deflection will definitely be the same at point K. So let's pick it yeah. So when this happens, you can see it's going to drag to cause a sagging at BC. So you have a sagging at BC this way than to C. Okay. Now, of course, if we have BC under sagging tension, we are going to have CD in a hugging tension. You see, it goes this way. So that this is going to be the deflected shape of this beam when a unit couple moment is acted at point K. All right. So this is the influence line for this particular beam at point K. So I say influence line diagram, ILD. So the influence line diagram, ILD, for point K. So what we want to determine, we are going to determine the deflection of this beam at point K. And in doing that, we will need to obtain the deflection expression of this beam at point K, where we have the deflection expression of this beam at point K. We'll find the exact deflection at that point K. Once we are able to get the deflection at point K, we will divide that deflection by the slope at point K. So once we get the deflection expression, we'll divide that expression by the slope at point K. So that will give us an expression for the influence line diagram at point K. Okay, so now we are going to go into that. Let's do it and let's see what we can do. So we'll pick the first portion, which is portion A to K. So let's consider A, considering A, beam A to K. Okay, let's consider beam A to K. The next thing we are going to do, get the reactions, the various reactions of this beam. We'll draw the beam and we'll obtain the reactions. All right. So let's go. Remember, we have arrow B. We can decide to pick whichever portion, but it is more convenient to pick portion A to K than to start from B, from K to D. But whichever you wish, but let's work with this most simplest one. So let's sigma FY0 for portion A to K. We have arrow A. Arrow A becomes equal to arrow K prime. So we say sigma mk is 0, moment about summation of moment about k. So we have arrow a times 4.493 equal 4.493 minus 1, which is our anticlockwise moment, is equals to 0. So we have arrow a becomes 1 over 4.493. We do that, we have 0.225 kilonewton. So this becomes our reaction at point A. All right. This becomes our reaction at point A. So having gotten the reaction at point A, we'll equally know that arrow A is equal to arrow K prime. So definitely we've gotten our arrow K prime to be equally 0.2225 kilonewton. So we've obtained the various reactions in the beam AK. So the next we are going to do is to is either we obtain the reactions for K to D, or we write the moment expression quickly and we'll continue. So let's have it this way. Let's go from D to K. Okay, this is what we have on the board, D to K. All right. So if we turn in the other direction, you will see it as this. So you see it as this from D to K. Now let's consider D to K, and let's see how we can obtain our expression. Now we know summation of sigma y becomes 0. So we have arrow D plus arrow C plus arrow B plus arrow K equal to 0. All right, equal to 0. So this is one of the equation for the beam D to K. So we have arrow D plus arrow C plus arrow B equal to 2 to 5. Okay, so arrow D plus arrow C plus arrow B equals to minus 0.225. Remember that arrow K from the previous drawing, arrow K prime is equals to arrow K prime prime, which is what we have on the other side, D to K. Okay, so we can call this equation 1, like we've done now. So let's say sigma F equals sigma mk, summation of moment about K to be 0. So we're going to have arrow D times what we have there is 35.507 total length, plus arrow C times 25.507, plus arrow B times 5.507. We have a moment, which is a moment of -1. So we have minus 1, all equal to 0. So we're going to obtain the second equation. So if we do the second equation, we're going to have, we're going to have 35.507 RD plus 25.507 RC plus okay, so we have 5.507 RB all equal to all equal to 1. So this is the second equation we have obtained for this beam D to K. So we have a second equation. Now the next, we can write this equation as this, 25.507 ROC plus 5.507 RB equal to 1. So let's call it equation 2. So I haven't gotten equation 2. Remember, as it is, we have 1, 2, 3, 4 unknown. So we can say determining moment expression so we needed to obtain the moment expression for this beam D to K. Okay, so let's redraw it. Here we have ROD, ROC, ROB, and the last so we have ROK and an anticlockwise moment of 1. So let's take an arbitrary point to point BK. So let's call it X. Okay, let's call it X. So we have a moment about that point. Let's take a section across the beam. So the moment expression becomes RD times X plus ROC X minus here is 10 meters. Remember, here is 20. Here is 5.507. Okay, so it becomes ROC minus 10 become plus RB minus 30. RB minus 30. Minus 30. Okay, so there's a moment expression. Take a moment about any section along BK. So we say moment expression becomes equal to now we have the moment expression. We can get the slope expression and the deflection expression for this particular beam at that section BK. So the slope expression, we have the flexural rigidity. Slope is a function of x, so we have it integrated. So when we integrate, we'll have it as this RB. So we integrated it. So let's integrate. We have an integration constant. Let's call it C1. Okay. Now we're going to integrate further to get the deflection expression. So we have the flexural rigidity EI, where Y represents our deflection, is a function of X. So we have ROD X raised to power 3 over 6 plus ROC X minus 10 raised to power 3 over 6 plus RB x minus 30 raised to the power 3 over 6 plus our C1 from our first integration plus our C2. Okay, so this becomes the deflection expression for this beam at a section across span B to K, starting from the left hand side, which is from support D. So these are deflection expression. So the next we are going to do is to obtain the unknown. Of course, for us to obtain the unknown for this expression, we are going to take boundary conditions. And the boundary conditions are obvious. Remember that for a simply supported end, which is our support D, deflection is 0.